problems, but no answers. Now, the point of the mini prints is really to help you, because that means that instead of having to write down all this stuff that I'm saying, you can just take a little mini print and take little notes on it, annotate the thing. Question? Yes. The first one I gave you because you didn't know about it, right? But after that, it's always going to be on Blackboard, and you should go to Blackboard, download, and print before you come. Well, we have a problem that you need to work along with me. The answer, of course, is not there. And so what you do is you write very, very small and fill it in. As I teaches you to write small, very good talent. Any other questions? All right, so let's just do our quick review of general chemistry. And we're going to take general chemistry, and as we do this, we're slowly going to be applying it to carbon compounds. But let's start at the very beginning. We all know what atoms look like, and it's not this. This is straight from Jimmy Neutron or something like that, Big Bang, whatever. The modern description of the atom doesn't have the big nucleus and little electrons and orbits. It's basically a cloud with a little tiny nucleus in the middle. This represents carbon. Carbon has basically 6 protons, 6 neutrons, and has electrons in 2 clouds surrounding it. Now we'll talk a little bit about these in a minute. The core electrons, these guys in the middle, they don't do anything. The outer electrons, you'll recall from general chemistry, are the valence electrons, and these are the ones where all the chemistry happens. Atoms are incredibly small. If we had a copper penny, there would be roughly 28 sextillion atoms in that penny. Now, of course, this is in copper. It's just very, very thin layer of copper, I think 0.08%, but nonetheless, if we had an old penny that's 90% copper or so, it would be all be copper atoms. Mass of a proton is very small, 10 to the minus 24 grams, neutron just about the same, electrons much less. And basically that means that the mass of an atom is concentrated in the nucleus. And the rest of it is basically just empty space. Now when I made this slide, I put the little dot there. There is 1 pixel. That's supposed to represent our nucleus, but even that's a bit distorted. This is Wrigley Field. You may recognize it. And if you look very, very hard, right here on the infield, right about there, I'll put a golf ball. There it is. If this was a nucleus, let's say a carbon atom or something, and we placed it there on the infield, this would be our nucleus, and the entirety of the stadium would represent the electron cloud. So virtually all the mass is down there. This is all essentially empty space. Kind of amazing, actually. All right, we all know what elements are. They all have individual symbols, and we arrange them in the periodic table. Periodic table has 18 groups going across. We tend to focus on 1, 2, and 3, 4, 5, 6, 7, 8. This is carbon, average atomic mass, again based on isotopes. This is the periodic table according to organic chemists. Basically, organic chemists ignore most of the periodic table and only focus on the handful of compounds that actually bind to carbon. a little bit of a joke, but really this is all you need to know in terms of elements in organic chemistry. I mentioned the atomic mass. Average atomic mass of carbon was 12.01 because of isotopes. Once again, here's our core, here's our valence. If we take, oh, okay. I guess I decided not to do that one. Let's see, let's go back to that slide. Okay, backwards isn't working. I don't know why. Let's go back to this slide. Okay, we talked about the electrons in carbon being distributed in two energy levels. These quantum levels that they're called are actually described very nicely just by the periodic table itself. The periods in the periodic table basically reflect the quantum levels. Groups going across, and periods, of course, going down. In every period, you can have 2 n squared electrons. That means our first period can have a total of 2 electrons. Second period here, 8, 18, 32, 50, whatever. Within each of these quantum levels, we can arrange electrons in orbitals. The simplest is spherical symmetry, that's the s orbital. Next we have, and again, each orbital can only hold 2 electrons. Next we have our p orbitals. These are lobes oriented x, y, and z. And after that, we do d's and f's and whatever. Now, these are just really cute to look at. If you just look at some of the geometry here, that's just amazing. But again, they each can hold 2 electrons. With carbon, we're only dealing with s and p's. Most of the things that we're going to react with won't go past the d level. Maybe my battery is low. If you look at the periodic table, our first period, we can put 2 electrons. They're in the 1s orbital. That's hydrogen and helium. Go to our second. Our first 2 electrons will go in the 2s. The next 6 electrons will go over here in the p orbitals, the x, y's, and z's again. Third, the same way, we're going to put 2 in our s. There are d orbitals here, but they actually don't show up until we get here because the 3d orbital is higher energy than the 4s. So the next electrons we put in are over here in the p's. And then finally we get to this set here. Again, these don't fill because they're higher energy. So in our fourth period, we're going to do 2 electrons here. We'll fill up our d's finally. These are the 3 d's. And then we'll put the last electrons here in the p's. As we put these electrons in, remember every orbital can accommodate only 2. And we put these in with opposite spin. You recall that when we spin an electron, we generate a small magnetic field. Now this is actually not a real spinning thing. Okay, this is the quantum property called spin. But it sure looks a whole lot like these things are spinning. And when they do, they can orient themselves in 2 ways. So the 2 electrons that we place in an orbital are going to have opposite spins. So let's go to hydrogen. That's our very simplest. That's our first period. We have 1 electron, and it goes in the 1s orbital. And we assign it a spin. helium, 2 electrons. One is going to be spin up, and the other must be the opposite spin. Abbreviate this as 1s1 and 1s2. Again, you're just simply supposed to know that these 2 electrons must have opposite spin. Any questions? Hopefully this is all just review of general chemistry. All right, let's go ahead and use carbon as an example. And why don't you just write the electron configuration? Look at our periodic table here. We're in row 2, and we are atomic number 6. Well, because our atomic number is 6, that means we must have 6 protons and, of course, 6 electrons for dealing with a neutral carbon. Of our 6 electrons, we're in our second period, so our first level is full, that's 2. And our second, we're going to put 2 electrons here in the 2s, and then we're going to have 3 p orbitals. Remember, Hund's rule says that we have to put these things in one at a time, and they will go in with the same spin, and then they will pair with opposite spins. So, doing the configuration, we would start with the 1s, and it's full. 1 up, 1 down. Our 2s is also filled. 1 up, 1 down. And our 2 p orbitals, we're going to have 3 of them. We will put 2 electrons, there they go, and they will again have the same spin, but only one at a time until we fill up all of the orbitals. Any questions? Now once again, this is all really basic stuff. If anything we said here didn't work with you, it's been a while since you've had general chemistry or something, there's this is the full configuration, and we would abbreviate this as 1s2, 2s2, 2p2. Again, understanding that we know what Hund's rule is, and that these are separate electrons. All right, like I said, if you don't understand any of this stuff, this is just a place that you can go and review some of the fundamental concepts. This is chemistryonline.com. That's my site. It's actually written for intro chem, but there are lots of things here. Again, this all goes to very basic whatever. But tutorials, those are little 5-minute movies about a subject. So if you just need to review something like that, you could go there. The tutorials here, you just might look at those. We're going to use this for a quiz later, but they are actually kind of neat. They're algorithmic tutorial problems, and mostly, general chemistry sort of stuff. But every time you take one of these, every time you pull up a new problem, it generates new numbers. So it's totally algorithmic. They're actually kind of neat, very nice review things. So that's Chemistry Online, and look up. These are the tutorials, the little movies. Again, they cover basic things, but if there's anything that you need review on, it's a place to go. All right. Let's start building some very simple molecules. And we're going to do this using the concept of Lewis dots. Lewis figured out that in order to describe the bonding in many compounds, including carbon compounds. A very simple device to do that was to use little dots to represent valence electrons. Now, carbon, we said, is in the second period and has 4 valence electrons. Lewis said we start off with the symbol for the element, and then we were simply going to place the electrons around it as simple dots, and we put them in unpaired until we get 4, and then we start pairing them up. So for carbon, we simply show the symbol and 4 little dots around it. More than 4, again, we pair them up. Let's just make sure we can do that. Go ahead and do fluorine for me. Fluorine is over here. It's also in the second period, and it's in group 7. Because it's in group 7, it will have 7 valence electrons. We'll start off with the symbol, that's an F. And now we must put 7 electrons around it, put them in singly, and pair them up. Remember that this is simply a bookkeeping device. It doesn't matter where your unpaired electron is. It's not real anyway. But it's just a nice, simple, happy bookkeeping device. Now, Lewis said that we could describe covalent bonds using this. For example, for chlorine is Cl2. Also group 7, so we have 7 valence electrons. To form a covalent bond, what we simply do is move the other chlorine in. Remember, we share electrons between the 2 chlorine atoms such that each of them has an octet. Remember, you count the shared electrons twice, so this guy has 8, and this guy has 8 as well. In organic chemistry, we will probably not draw very many little dots. We will show our covalent bonds simply using our dashes. Remember, the dash tells you that this is a covalent bond where we are sharing 2 electrons in that bond. Any questions? All right, let's just build a simple molecule here. Go ahead and do ammonia. For ammonia, you want to find the nitrogen. It'll be in group 5. Then you want to find hydrogen, that's group 1. Our nitrogen, of course, is a central atom. And we place the hydrogens around it so that we have an octet on the nitrogen and 2 electrons, which is the most we can hold, around the hydrogen. There's our nitrogen with its 5 electrons. 2 of them are paired. We have 3 hydrogens with 1 each. All we have to do is snuggle these guys up. These are going to be our 3 covalent bonds, and nitrogen has 1 unshared pair. Again, we have 8 electrons around our nitrogen and 2 around each of the hydrogens. Organic chemistry, we would kind of draw it this way. The organic equivalent of ammonia is going to be an amine. And it's important in this case to remember and recognize that we have the unshared pair, because virtually all of the chemistry, all the organic chemistry of nitrogen compounds resides in our unshared pair of electrons. Any questions? Well, okay, Lewis addressed the question of valence. Let's just remind ourselves with some very common compounds. When we talk about valence, this is the number of bonds that a element will typically form. These are covalent bonds. For oxygen, we have 2, and we have 2 unshared pairs of electrons. Nitrogen, we just did, we have 3 bonds. Boron, we also have 3 bonds, but we don't have an octet, do we? Because of that, boron is a really powerful Lewis acid. And we will take advantage of the Lewis acidity of the boron when we do reactions involving boron compounds with organic compounds. Carbon, of course, has a valence of 4. Now, we talked about the electron configuration of carbon to give us our valence of 4. Remember, we have our 4 valence electrons here. 2 are in the S and 2 are in the P. You actually might look at that and wonder how in the world we're going to make all of these bonds. We could simply put electrons here, here, and a pair in here, but that would be kind of funny. What we're actually going to do is to take these and split them up. We're going to demote one of these guys to a p orbital, so we have 4 equivalent electrons here. Now, this gives us 3 in p orbitals and 1 in an s. You could argue that because the s has spherical symmetry and the p's have lobes in the x, y, z axis, these 3, that the bonds to carbon of our 4 bonds are all going to be different. All 3 will be the same and 1 will be very different. This occurred to chemists a long time ago. If you combine spherical symmetry here and then x, y, z symmetry here, you would expect, well, unique geometry. Chemists back in the old days, before they had computers or X-ray, anything like that, they were really smart. They were really good. And they figured out that carbon was tetrahedral based on very simple arguments. Let's just relive this moment. We could take our valence of 4 and we could arrange it in at least 3 ways. We could do square planar. We could do trigonopyramidal, or we could do tetrahedral. Now, squares and pyramids are taught in kindergarten. Nobody ever teaches tetrahedral in kindergarten. I don't know why. Very important. The way that they did this, now this is, way, way, way back, was they simply asked how many different isomers of something like dichloromethane could you form from each of these structural geometries. Okay. Starting over here with square planar. We could put our 2 chlorines opposite each other. That's one. Or we could put them next to each other. So we would expect at least 2 isomers of our dichloromethane. My battery is dying. Oops. Okay, all right, hang on. Okay, so we would expect at least 2 isomers here. If we had trigonopyramidal, we could put 1 axial, 1 equatorial, or we could put 2 equatorial. So again, 2 isomers. However, if carbon was tetrahedral, these 2 are next to each other, and they're 109 degrees apart. If we move down here, they would also be next to each other and 109 degrees apart, and the same thing with these 2 here. So we would only get 1 isomer if carbon was tetrahedral. Very simple logical argument, and the conclusion, and they were right, carbon is in fact tetrahedral, and all of these are equivalent bonds. Now, you can predict that this is methane, 1 carbon. You can predict that using valence shell electron pair repulsion theory. Basically, what it says is you start off with 2 things around. The electrons are going to always arrange themselves so that they're as far away as they can be. Tetrahedral works. So when you put 4 things in, the electron pairs get as far away from each other as they can, and that generates the geometry. Another approach to the thing is called hybridization, and that's simply a quantum mechanical tool where you do the same sort of an argument. You take the geometry of the S and the geometry of the P's, and you say, we're going to combine these into the lowest energy possible. And that turns out to be hybridization, 4 equivalent orbitals, and we're going to call these sp3 because they are all constructed by hybridizing 1s and 3p orbitals together. sp3 is a nomenclature that you need to know because we're going to talk about sp3, sp2, sp, etc. 4 orbitals, 1 from the s and 3 from the p's. This is what gives us our tetrahedral geometry for methane. This is what's known as the highest occupied molecular orbital for methane. Basically, it simply is a shell of electrons surrounding it. Methane is hiding here in the middle. And this, when you do molecular orbitals, you're simply getting a description of where the electrons are in a given molecule. Any questions? All right, so carbon has a valence of 4. We're going to form 4 bonds. All the bonds are going to be equivalent. We're going to call these sigma bonds. Sigma bond is just a simple single bond. Let's go back to our Lewis description then. Go ahead and do one for ethane. Ethane is 2-carbon hydrocarbon. Again, we find carbon. It's in the 4th group. We know that it has a valence of 4. Each carbon here is going to be bonded to 3 hydrogens, and then the 2 carbons are going to be bonded together. That gives us our valence. So we start off with our 2 carbon atoms. Carbon with its 4 electrons, hydrogen with its 1. There's our 2nd carbon, and all we have to do to make our bonds here, again, is to simply snuggle up, convert these from lots of little silly dots into dashes, and when we see something like this, carbons with dashes around it, we are supposed to remember that each of these carbons is tetrahedral, that all of these are what we call single bonds, free rotation around single bonds. And again, they're both tetrahedral. Now, organic chemistry involves a bit of exercise for visual 3D rendering. We will look at projections, simple drawings. You are then required, in your mind, to be able to see these as they really are in 3 dimensions. This is going to be very important when we hit chapter 6, I believe, which is stereochemistry, where we talk about the actual spatial orientation of groups around carbons. This was fun. Let's do what's called ethene. Ethene is 2 carbons and 4 hydrogens. Once again, carbon is group 4. So we will put our carbon with 4 valence electrons around it. Each hydrogen, of course, has 1. Now when we scooch these guys together, we have 2, 4, 6, 7 electrons around each carbon. That's unhappy. And so to get our full octet, what we have to do is to take our extra electrons here, simply move them in between our 2 carbons, and we're going to make a double bond. So that's 2 covalent bonds, and we would show it like this. This is what ethene looks like. The valence shell electron pair repulsion tells us that these carbons should be trigonal. So these bond angles should be 120. And we have this double bond in between our 2 carbons. Now, let's think a little bit about where this double bond really comes from in terms of these S's and P orbitals that we're dealing with. In order to form our carbon-carbon double bond with trigonal geometry, we need 3 orbitals to work with, okay? We're going to use 1 S and 2 of the P's. We will call the hybridization, the trigonal hybridization, sp squared, sp2, okay? When we combine these things together, we form our trigonal geometry here. 120-degree bond angles, etc. So trigonal planar geometry. This is our first bond here between our 2 carbons. Now, on each of these carbons, we've used an S and 2 P's, but we have a P left over, don't we? So, if you put these p orbitals in, there's 1 on each one, and it'll look like that. Okay. The way I have these things arranged, these orbitals, remember orbitals are simply regions of space where electrons can reside. They are adjacent to each other, and they line up. Because of that, they overlap, which means that the electrons are shared between these p orbitals. What we wind up with is something like this. Looks like a hot dog of some sort. This is our hybridized orbital, where we combine our p's together. If we cut this open a little bit, you can see there's ethene hiding inside. Again, p orbitals above and below. So when we talk about a carbon-carbon double bond, One of these is our sigma bond, this one, the real covalent bond, and the other bond is constructed from these p orbitals, and we're going to call that a pi bond. Greek letter pi, we say we have a pi cloud above and below the plane. One bond is a real sigma bond, the other bond is a pi bond. When we draw something like ethene, we will not draw orbitals and stuff like that. We'll simply show two lines, but we're all expected to know that one of these is our true sigma bond, and the other is constructed from these p orbitals, and it's our pi bond. Now, the fact that we constructed this from these orbitals has a very interesting consequence. Well, this is what it looks like in what's called an electrostatic potential diagram. It's related to electron density, but really isn't. But it's colored. Electron deficiency is basically blue. Rich electron is red. And you can see in the region here for our pi bond, we have a nice red cushion. Lots of electrons. This is the functional group called an alkene. We'll deal with those again in a moment. But the reactions of alkenes virtually all occur at this pi cloud, where we have this excess pile of electrons. But let's talk about the interesting consequence. In order to make our pi bond, we had to line these things up so that they were parallel to each other, right? But the sigma bond between them is a real single bond, and because of that, it has free rotation. What if we took and we rotated around that so we were in this configuration? Well, turns out that when you get 90 degrees like this, the overlap integral, which means how much they share, drops to 0. So this is a nice low energy state, and this is a real high energy state. So what that means is this rotation doesn't happen. It does happen, but it happens with. That means that when we're dealing with compounds that have carbon-carbon double bonds, we can get isomeric structures that differ only in the placement of groups around our double bond. On the opposite side, we'll tend to call these trans. We'll change that later. On the same side, we will call these cis. And again, this is a simple example of what we call stereoisomers. And we'll deal with stereoisomers in great detail in chapter 6 or so. There's one more formal bonding in carbon that I'd like to talk about. And this is going to be what's called sp. For sp, we have two orbitals that we're using. So we arrange these in such a way. Again, valence shell theory tells us that we want to be 180 degrees to get everything as far apart as we can. Now, just like we had leftover p orbitals, here we're going to have lots of leftover p orbitals. Every carbon's going to have two, so if we put them around there, this is what it looks like. We can do the same trick now, can't we? We can overlap these guys, these guys, these guys, and the ones back there, and we can form pi bonds. We're going to form two sets, one like this, one like this. Actually, they will tend to overlap in such a way that it forms a continuum. when we talk about a carbon-carbon triple bond, once again, one of these is a real sigma bond, and the other two are these pi bonds. If you look at electrostatic potential map, again, you can see the band around the middle here where all the pi electrons are, and there's our carbon atoms buried in the middle. This is the functional group we'll call an alkyne. And again, the reactivity of alkynes is going to be regulated by the electron cloud here. It's a good Lewis base, so electron donor from the very rich center. In general, there are three things we talked about. sp3 hybridization. It's going to give us single bonds. We are going to have tetrahedral geometry, and we have free rotation. If we have a carbon-carbon double bond, that's sp squared hybridization. One of these is a sigma, the other is our pi bond. And finally, for sp hybridization, we have one sigma, and we have two pi's. Organic chemistry, we will talk about compounds like this as functional groups. The functional groups here that we're dealing with are going to be called alkanes, alkenes, and alkynes. The neat thing about organic chemistry is that if you have a compound with a carbon-carbon double bond, that this will undergo characteristic reactions. It really doesn't matter so much what you have attached around, but the double bond will undergo a set of simple reactions that you can predict and predict products. Same thing with the triple bond. So we tend to organize organic compounds into things that we call functional groups. And we're going to deal probably by the end with like 20 of them. There are just an infinite number of carbon compounds. But if you can understand the reactivity of a functional group, you can pretty much predict what any of them is going to do. So it makes it really easy. Nice way to classify. We will return to functional groups later. So this is just an introduction. And we're going to deal with these one at a time. Let's do a very simple little problem here. Let's look at this organic compound. And just look at these simple questions. Take your version of this, and again, writing very small. See if you can pick out the carbon atom in this that displays sp cubed hybridization. Well, sp cubed, we know that that's tetrahedral. We know that we will only have single bonds. So you're looking for a carbon here that only has single bonds. These are all double bonds. That's a double bond. This guy right here is the only carbon that is sp cubed. Our next problem, the CCC bond angle. So we're dealing with this one, this one, this one. What's the angle? Going boom, boom, and boom. Yeah, you gotta look at this. This is a carbon-carbon double bond, isn't it? So this is trigonal. 120-degree bond angle. All right, our next one. Find an oxygen with sp squared hybridization. Remember, sp squared is a double bond, isn't it? This oxygen has two bonds to it, two separate bonds. This guy is a carbon-oxygen double bond, which means that the carbon is sp squared, and so is the oxygen. We will refer to a carbon-oxygen double bond as a carbonyl. And carbonyls undergo a whole set of very characteristic reactions. Let's see the CCO bond angle. So that's CCO. Yeah, again, this is an sp squared carbon. So that's going to be 120, just like the other. And finally, how many sp squared hybridized atoms do we have in this thing?
7, 8.
Well, yeah, we have 6 in our ring here, don't we? 1, 2, 3, 4, 5, 6, 7, and 8. So a total of 8. This here is a carbon-oxygen double bond and the OH. This is what the functional group we call a carboxylic acid. Different molecule here. How many sp hybridized atoms do we have?
4.
We have 4 of them, that's right. These are all sp squared. This is our carbon-carbon triple bond. And this is a carbon-nitrogen triple bond. Again, they're all sp atoms. This is a 6-carbon ring. The geometry that it's drawn in is the lowest energy geometry for a 6-carbon ring. We will spend pretty much an entire chapter talking about the geometries of these particular compounds. But how many sp cubed atoms do we have here? Well, you just want to look and say, gee, there are no double or triple bonds, are there? So we are going to do all 6 in our ring here, that, and remember our nitrogen is also sp cubed. As a lone pair, don't forget that, that's the 4th thing around it that make it sp cubed. Finally, let's look at this guy. How many unshared pairs of electrons do we have here? In organic chemistry, a lot of the reactions we do are going to deal with things that have unshared pairs of electrons. If you recall, oxygen has a valence of 2, doesn't it? But because it's in, group 6, it must also have 2 unshared pairs of electrons. This oxygen also must have 2 unshared pairs, and of course our nitrogen has 1. Any questions? If you want to play with stuff like this, simple problems and stuff like that, this is an old page. On Blackboard, I will put the link up so that you can get there. It's a hidden link. Nobody else in the world is supposed to be able to get there, but So this is old. Back when we did McMurray's 6th edition, I wrote what was called Organic Chemistry Online. This was, first day, it was amazing. This is the Organic Chemistry Online, the old, that's the original version, kind of neat still. Later on, we redid it as Organic Interactive. If you click on this little guy here, it will take you to what used to be the Brooks Cole site. Now they call it this, and they call it Organic Chemistry Direct. But this is actually a window into, it's free, which is amazing. It's still up there. I don't think they know it's up there. But you can select a chapter from the book. Organic Interactive is the thing that you would like. And what you'll see is, like for structure and bonding, hybridization, line bond structures, stuff like that. You click on these guys, and there are problems and explanations and stuff like that. Now again, the technology is much older than we like now, but still it's a very nice way to review. Lots of nice things in there actually. So I will put this link up again on Blackboard. All right, let's talk about carbon compounds. These are some carbon compounds. The interesting thing about carbon is it forms chains with itself and with other things. And so you could just have immense variety in carbon compounds. Here we have 1, 2, 3, 4, 5 carbons in a row with a 1 carbon side chain. We've seen this. This is 6 carbon atoms in a ring. Here we have a ring, 7 carbon ring actually, with a couple side chains sticking up. This is another ring actually. Just amazing. We call this a polycyclic compound. We can also stick in what we call heteroatoms. Organic chemists tend to be very carbon-centric. So carbon is the normal, and anything else we will call a heteroatom, something else besides carbon. This is glucose. Glucose has 5 carbons in a ring, an oxygen bridging, a lot of OH groups, that's the alcohol functional group. This is morphine, polycyclic compound, nitrogen in there, oxygen bridge, a couple OH groups, etc. So you can put these things together in remarkable ways. Now I've represented these using a model. This is a ball and stick because it looks like little balls and little sticks. This is called a driving model. You can actually buy a model kit that looks a lot like this, where we just take the balls away and we just use our little sticks. This is what the same molecule for a carbon chain would look like, and all these are on the same scale. So we draw these like this, but this is what it really looks like. This is very nice, very instructive, but none of us have the artistic ability to draw these things, do we? So we have to find some way to represent carbon compounds quickly and simply. The simplest way, of course, is our molecular formula, but that tells us nothing about the molecule. This is our ball and stick model, we can do a little bit better here with what's called a condensed structure. Now in a condensed structure, we're going to draw out, or at least label, the things that are attached to each carbon. As you draw it and write it this way, the assumption is that these carbons are going to be bonded together. This carbon is then going to be bonded to 3 hydrogens, 2, 2, and again 3. So this does give us some simple structural information. This is, well, it's actually called a Kekulé structure, but it's based on Lewis. And again, we have little dashes. This is nice because it just shows all the bonds, but it's a real pain. It is just very difficult. And you just get so tired of little dashes and hydrogens. So organic chemists reduce that to a stick. Now when you draw a line drawing, you are again making the assumption that whoever sees this knows that the line coming off and terminating like this is actually a CH3. If you have a vertex, it's a CH2. This is largely how we're going to represent our carbon compounds, using line drawings or derivatives of those. Now, this is our strict line interpretation. We're going from our 4-carbon chain to this. Again, both of these are CH3s, both of these are CH2s. Sometimes, however, people will try to help you along. And so they will take these terminal guys and stick on CH3s. Trying to help, right? Some people, however, look at this and say, but this looks stupid because it looks like the hydrogen is bonded to it. So they'll take it and they'll reverse it. But then you have to write H3C, and that just sounds a little silly. You will see all of these combined in our various representations for carbon compounds. Once again, if you don't see anything, that is a methyl group or a CH3. Again, sometimes these are written out to help you, but you just interpret it. There are a couple other ways that we tend to draw things. This is our modified line drawing for, again, our 4-carbon chain. If we take this guy and we turn it so that this carbon atom here is facing towards us, we get what's called a sawhorse projection. Again, this is this carbon. The CH3 is pointing up, and remember we have 2 hydrogens. That's those guys. Why do we worry about things like sawhorse projections and whatever? Well, remember I said that we're going to do a great deal of geometry, structural, spatial geometry in organic chemistry. And so it's important to be able to draw these things in different representations. We can take this all the way and make what's called a Newman projection. In a Newman projection, we're basically rotating this such that we're looking straight down this axis. So this is our front atom. The back atom, just so that we can keep track, we draw as this big circle. The little guy is in front, and the big circle is in the back. The transition between all of these, this is a movie I made years ago, but this is our simple stick here. Let's see if it wakes up and does it by itself. Oh. Well, the movie is not going to run. Shoot. If the movie ran, you would be able to see this is our front atom in our Newman. This will be our back atom. I'll try to fix this movie. The way they have the computer system set up here, movies in PowerPoint don't always play. Oh, it's going to run. Okay. All right, let's watch that again. There it goes. We can move this forward. That's our sawhorse. And finally, that's our big back atom, and that's our front. We will use Newman projections and sawhorses as we investigate the structural geometry of carbon compounds. All right. Let's go ahead and do a simple exercise. Take these structural drawings of some sort and convert them into line drawings. This is a real exercise. This is the kind of thing that you're going to do. It's going to be so automatic, it's like breathing. For our first compound here, we look at our condensed formula. That's a CH3 on one end. It's going to be bonded to this carbon. This carbon is in turn bonded here. There are two CH3s attached to it as well. Another CH2 bonded to this CH2 to a CH3. So we have a chain of 1, 2, 3, 4, 5 carbons. And on our second carbon here, we have two CH3s. Now, why do we draw this stuff as a zigzag? Well, it's an attempt to represent the sp cubed or tetrahedral geometry of the carbon. So we draw them as zigzags. This, of course, is not ziggy or zaggy. Here's our 6-membered ring. We will call this cyclohexane when it's time. Go ahead and draw this as a simple line drawing. All you need to do is just look at this thing and then connect all the carbons, except don't draw any of them. When you do that, it looks like this. Again, it's zigging and zagging because these are all tetrahedral carbons. When we do cyclohexane, we will call this the chair conformation. If you look at it and you have an imagination, you can see this as kind of like a lawn chair. And finally, let's take this Newman and untangle it. Let's look for our chain, our longest chain. It's going to be 1, 2, 3, that's our front carbon. 1, 2, 3, our back carbon is 4, then 5, 6. So we have 6 carbons in a chain. All right, on carbon number 1, 2, 3, we also have a CH3 side chain. On carbon 4, we have another CH3 side chain. Carbon 3, carbon 4. Let's do this step by step here. Here's our original Newman. If I take this and draw it as a sawhorse, it would look like this. Again, there's our front carbon, 2 carbon chain, CH3, 2 carbon chain, CH3. It goes back to the back carbon, which is here, and a CH2, oops, CH2, CH3, and another CH3 is all attached. Finally, converting this, here's our parent chain, our longest chain, and our 2 1-carbon side chains. All right. Well, hopefully by now, we can now draw these things, right? You can look at me and, pretend this was test time or something, and say, well, gee, what if I had drawn this, different? What if I had the orientation different or something like that? That would be perfectly fine. Because remember, all of these guys are single bonds. This is a 5-carbon chain, and it's doing gymnastics. It's supposed to represent, let's see if we can make it do it again. It's supposed to represent the dynamics of a carbon chain. All these bonds can rotate. So basically, any way that you draw this thing is a reasonable structure. Another way to look at it. Here we have a 1, 2, 3, 4, 5 carbon with a 2 carbon side chain. We could draw it this way, we could rotate it, draw it this way. Draw it any way you want, as long as you have a 5-carbon chain with a 2-carbon side chain. These are what we call conformational isomers. In general, conformational isomers interconvert so fast at room temperature, just like we saw with our little movie, that any one you draw is the same. Now there are energy differences, and we'll address those, but typically we were just going to draw these things any way that we can. Now please, on an exam, when you draw your structures, draw them beautifully, because somebody has to look at them, that's me, and figure out what you're trying to draw. So spend a little bit of time and learn how to do this. In fact, let's go ahead and draw some now. Go ahead and convert these into nice, beautiful line drawings. Our first one, we have a carbon. Our longest chain here is going to be 3 carbons long, 1, 2, 3. On our middle carbon, we're going to have 1 carbon side chain and a bromine attached. We'll call this an alkyl bromide a little bit later. That's the functional group. And we could draw it simply like that. Once again, you could draw this any way that you want, as long as you have a 3 carbon chain, 1 carbon side chain, and an halogen. This next one, our longest chain is going to be 1, 2, 3, 4, 5 carbons. 1 carbon side chain. Something like that would work. Our next one, we look for our longest chain. Once again, it's going to be 1, 2, 3, 4. 1, 2, 3, 4 carbons. And here on this second carbon end, we have 2 1 carbon side chains. Something like that would work. Let's do another set. Here we have carbon-carbon double bonds. As we draw these, remember we try to represent our trigonal geometry. So, because it matters with a double bond especially. So, draw these and preserve your geometry there. Well, we're going to look for our longest chain here again. It's going to be 1, 2, 3, 4, 5 carbons long. We're going to have 2 carbon-carbon double bonds. Remember, in a line drawing, we don't have to show hydrogens. So that works perfectly well, doesn't it? We look at this. This is a truncated set of lines. We know that that is a CH2 now, because carbon must have 4 bonds. Here's our 2 CH3s. I've stuck the bromine down instead of up, but it doesn't matter, does it? How about this guy? We have 1, 2, 3, 4, 5, 6, 7 carbons in a row. That's all you have to do. 1, 2, 3, 4, 5, 6, 7. Here's a sawhorse. Take the sawhorse and make a line. Draw it. Really, what you have to do is simply identify your longest chain again, don't you? We'll see that when we're dealing with these types of compounds, first thing you do is always look for the longest chain. So here we have 1, 2, 3, 4, 5, and we have a 1 carbon side chain on carbon 3.
The longest chain one more time?
Well, I did 1, 2, 3, 4, 5. And this guy, strange looking beast, isn't it? We have 6 carbons in a ring. Now wait, that should sound familiar, right? We can represent a cyclohexane a couple ways. Remember we did it as a chair. You can also simply draw it as a perfect hexagon. Again, I stress perfect hexagon. And finally, let's take this cyclic alkene and represent it. This is called cyclooctatetraene. What you must do here is draw a perfect stop sign and simply place double bonds in the appropriate positions. Now later on we will see that this is actually not a flat molecule as we've drawn it. The 120-degree bond angles require that this be distorted, and it's actually a basket shape. All right, that's pretty much going to wind up chapter 1. In order to stay on track, I'm going to go ahead and start on chapter 2. We'll do the first half of chapter 2. Would you like to take a 5-minute break? I mean, I can talk for hours, but just take